Okay, hello everyone. This is Dr. Wael. I hope you're doing well during the, Corona crisis. You're staying at home and you're keeping your social distance. I will be delivering the content from lecture 7 all the way till the end of the semester via a recorded session, just like this one. And I will announce other means of communication later on in the week. Okay. So let's start. What we have been doing up to now, we have been actually studying this part of a database engine, how the indices are created, what kind of indices exist in a database engine, which index to use, depending on the type of query you have. And what we're going to do is we're going to move now to this block, which is the query processor. What happens inside the database engine when it receives a SQL query that you've written, and the processing that happens to the SQL query is the responsibility of this module, the query processor. It's important to learn this component because based on what you learn here, you will start thinking of SQL queries in a different way. Once you understand the kind of optimizations and the kind of heuristics that might be applied here, and we will talk about that soon, you can actually write better SQL queries. Now, what's the issue? Why is this component so important in the database world? What you write in a SQL statement is a fourth generation program, or it's a fourth generation language. What that means is you write what you want, but you don't write how to actually retrieve the data. You don't specify in the SQL, okay, go to this table and open it and run this loop. You don't write loops in SQL because, again, it's a fourth generation language. Those of you who took the concepts course, they would have seen another fourth generation language, which is Prolog. You declare your intention, or you express your desire, basically, as if it's English, like, select star from this table where so and so, but you don't specify the details. You don't specify how this runs. Now, this is good in one aspect, that it makes us write queries easier, because it's just, we don't care about the details, we just express what we want, just like in Prolog. But there is a problem. The problem is for the database engine, now how to run this and how to run it optimally. So what actually happens inside the query processor, there is a number of transformations that happen to your SQL statement, and the goal of those transformations is to pick the optimal way to run your query. What you write in a SQL syntax gets processed first by the SQL parser. This module exists in all programming languages, whether they are a fourth generation language or a third generation language like Java and C# or C++. You have this module called parser. Those of you who will continue in the CSAN curriculum, you will take a compilers course in the 10th and 9th semesters. There is a lab and a course for compilers, and you learn actually how you build parsers. But for our purpose here, what I want you to understand is that the text you write, which is the SQL, will be translated to a tree. That translation happens inside the SQL parser. Now, this tree is fed into what we call the logical plan builder. And the purpose of the logical plan builder is to decide on the best logical plan that corresponds to your query, but it is an optimal logical plan, which gets fed later on to a physical plan builder. And the purpose of the physical plan builder, the goal is to, again, decide on the best way to actually run your logical plan. So it outputs what's called a physical plan. And this actually is what runs. So it's not your SQL that you've written, it's something else inside the database engine. This is the module that actually runs your physical plan. And this is the module that will produce the result set that you retrieve in your program, or you see on the shell if you are manipulating the database directly. Okay? So there is a number of transformations that happen from SQL to parse tree to logical plan to physical plan before you actually start seeing the output in the result set. So we're going to study this module and this module because the optimizations and the way actually things work inside these modules, your understanding of them will impact how you write SQL, and it will impact also how you will learn how to optimize basically database engines. Okay, so this is an example of what I'm referring to. If you write this simple query on these two tables, stars in and a movie star. So in the movie star table, you have a list of movie stars or tuples, where every tuple is a movie star, is the name of the movie star and his birth date and so on. And in the stars in table, obviously there will be other tables here if we're building this for real. There will be a movies table, for example. But I'm only showing here the two relevant tables to my query. The stars in table will have a title for the movie and the star name is this name. So they are linked by some, foreign key, the two tables. Now, if I want to find all the movies with stars who were born in 1960, I'm going to write a query that looks like this. Select title from stars in where star name is in this, okay, like 1960. Now, this is again an example of what I'm referring to. It's a fourth generation language. SQL is a fourth generation language. You don't say how you retrieve the information. You just say the information you want to retrieve. So this will be processed by a SQL parser, and the output from the SQL parser is what we call a parse tree. This applies to all programming languages, as I've mentioned before. What you see in the leaves of the parse tree are actually the program you've written or the statement that you've written, which is highlighted in blue here. And what you see above the leaf is some intermediate nodes that have meta information about what's the leaf. So the title, it's actually an attribute, which is part of a selection list. Okay, the stars in is a relation name, which is belongs to the from list. Okay, now in the compiler's world, you will know or you will learn names for these things. These will be called tokens, the ones in blue. Okay, or terminals. And the ones that are not in blue, or the ones above it, the ones that are not at the leaf level, will be called non-terminals. But we don't care much about here, about this, but just to give you some insight into compilers. Always at the leaf level, you see a program. Okay. Now this is actually the module that checks that you haven't made any syntax errors, for example. Okay, and this is the module that will tell you you've missed a semicolon at the end of the line. Okay? But again, this is not really our purpose here. Now, what I want you to understand is this will be fed to a logical plan builder. So let's understand the difference between logical plans and physical plans. See, a logical plan for the query that we were looking at is just displayed here on the left. It's nothing but relational algebra tree. So this is something you've learned in database 1. Okay, this is a select, Cartesian product, select, and this is a project. Okay, so logical plans are nothing but relational algebra tree plans. Physical plans, however, they look like logical plans. Obviously they have to, because they are just another way to talk about the same thing, the same SQL, but they will actually be consisting of what we can call as steps or blocks that are processed always from bottom to top, making a tree of actions. And these are the actions that actually gets executed by the physical plan processor. Okay, so you see here, like the relation movie star is appearing in, at the bottom here in the logical plan, and obviously it appears here in the physical plan. Okay, the difference here is, if you notice, the logical plan has no mention of how things run. While in the physical plan, we start seeing that. Okay, I'm going to do here an index scan on movie star. And here I'm going to do a table scan, which is basically a linear scan. Okay, So this is like O of n, and this might be like O of log n if you're using a b plus 3. So in the physical plan, we decide on how actually we're going to do it. Okay, and we will talk, in detail about how this is constructed later on. So the takeaway here is that database engines perform three translations to a SQL query: parsing, logical, and physical. Parsing is for syntax checking to make sure that you've written correct SQL. Logical and physical for optimization and execution purposes. So let's start with the logical plan builder. Again, the input here is a parse tree, and the output is a specific logical plan. Why am I mentioning or saying a specific logical plan? Because even if you think of the simplest queries that you could ever write, something like this, select distinct p from r, s, where r dot a equal to 10. So here is, join r and s, select a equal to 10, and this is the distinct operator. So even for this very, very simple SQL statement, I could generate a number of alternative logical plans or relational algebra trees. All of them will produce the same result, but they are different in terms of execution time. So I could start with R and do the selection early on, a equal to 10, since a is in R, and then I do a distinct, and then get the S, do a distinct, and then do the join. Or I could do the same thing for R, we'll do the select with a equal to 10, then join with S, and then postpone the distinct operator to the next level. So here's one alternative, here's a second alternative. And the question is, which one is actually going to be faster to execute? And this is the purpose of the logical plan builder. There are many logical plans. The question is, which one is the best one? And the best one here, the criteria is, which one will be faster to run, faster to execute? Okay? So for even a simple SQL, there are several alternative relational algebra trees. All produce the same result set, but one of them only will be the optimal one. Okay? So we will actually spend today talking about query optimization in the logical plan builder. And there are really, two types of optimization techniques or optimizers. Historically, the first one that appeared is called heuristic-based optimizers. And because of limitations to heuristic-based optimizers, we will discuss them first. Cost-based optimizers became the more common approach. But the two approaches do exist because there are some database engines that are still using it. There will be mostly historical database engines or older versions of database engines. So you need to learn about them. But more modern database engines would use cost-based optimizers. Now, it's not really either or here. Some database engines would do most of the time cost-based optimizers, but they also implement sometimes heuristic-based optimizers. And you will need to learn about the database engine and how it's built to know for a specific database engine how the optimization is really happening. Okay, and the really advanced database engines like Oracle and PostgreSQL, they would enable you to do some level of manipulation on how the optimizer work. Because as we will see in heuristic-based optimizers, some decisions are made that are not necessarily correct, or at least they're not really taking the different aspects that you need to consider when you actually make the optimization. Okay? So let's start with heuristic-based optimizations. Now, the word heuristic means like a rule or a standard, or a convention, if you'd like. Now, there are really three basic heuristics that historically have been developed, and they are very common sense rules. I mean, there's really nothing deep about them in terms of what they're trying to achieve. Okay? The three simple heuristics are: you perform the selection as early as possible, you perform the projection as early as possible, and you perform the joins and selections that enable you to reduce the result set size as early as possible. The idea here goes like this. The logic behind this is like this. If I would like to run a query as fast as possible, then the most straightforward way to do that is to be working with the smallest number of rows as soon as possible. So the earlier I reduce my data set, the set of rows I am supposed to be working with, the earlier the better. Okay, and this is really the rationale behind the 3 heuristics or the 3 rules. So let's look at one at a time. So the first heuristic says, push the selection down in the relational algebra tree as much as you can. So let's look at this sample query. It says select account.customer name from branch, account, depositor. So I have 3 tables. This is part probably of a banking system: a branch table and an account table and a depositor table. This will have all the branches for the bank. This will have all the accounts created by customers, and this will record every time someone makes a deposit. So the assumption here obviously is that every account will belong to some branch and every depositor will have some account. So people cannot just walk in and do a deposit in the bank. They have to have an account in the bank. Okay? So what the query is doing is retrieving the customer names from the account table where the customer is actually having an account with the Brooklyn branch. And this is how we do it. We say where branch.branch city equal to Brooklyn and branch.id equal to account.branch ID. So there is in the account table, there is a branch ID. So and this is referencing the branch.id, and the account ID equal to depositor.account. Okay, so the heuristic here says push the selection down. Why? Because selection means you're going to open a table and consider tuple by tuple, or maybe use a B+3, whatever. We don't talk about actually how this is done here. Remember, this is a logical plan. There's no mentioning of indices here. But basically, I'm going to go to this table and somehow do a select. So if the table has 10,000 rows, after the selection, I will have 500 rows, say, out of the 10,000. So the rationale here is, if I push the selection down in the relational algebra tree, I will reduce the number of rows I'm working with. And these rows are not necessarily my final result set, but if I make this reduction early on, then what I propagate upward in the relational algebra tree is going to be a smaller data set or a smaller subset of the data, which means the query will run faster, because if you're iterating on 500 rows, it's actually much faster than iterating on 10,000 rows, because you're just doing 500 instead of 10,000. So the idea here, after you've walked through the parse tree and created your first initial relational algebra tree from the parse tree, look at the selections and try to bring them down. So here I am selecting branch dash city equal to Brooklyn. Well, if in my first initial relational algebra tree, I'm doing the joins first and then join branch. First I will join account and depositor, and then the result I will join it with branch, and then I do the selection later on. But that means I will have lots of rows propagating upward. So to decrease those number of rows propagating upward, I will take the selection and apply it to branch directly here, down here. So this is what you see here, on the right side, that I have taken the selection down. Okay, and this is what this rule is all about. Okay, so I still join account and depositor, but I will not join it with everything in branch. I will join it with the output of this selection. So I will do the selection first, and then I do the join, which is over here. Okay, and this is what the heuristic is basically saying. Here is another example of pushing selections down. In this case, I made the SQL statement we were looking at a little bit more complicated. I just added one more selection criteria, which is account.balance less than 1,000. So applying the rule of pushing selection down should be done as many times as we can. So in this case, I'm having now 2 terms that I am selecting according to. Branch dash city equal to Brooklyn and balance less than 1,000. So I will push branch dash city equal to Brooklyn down to the branch table, and I will push balance less than 1,000 down to the account table. The effect of that is just similar to what we described in the previous slide, I am propagating upward a smaller number of rows in my result set or intermediate result set. So whatever I'm going to join as a result of doing the selection first between branch and account, intermediate results, is going to be much smaller than without having the selection pushed down. So generally, we consider the tree on the right as being more optimized than the tree of the left because of the effect of selection. The second heuristic is to push the projection down for the same rationale. Just like we pushed the selection down, we reduced the number of rows we are propagating upward in the tree. If the select statement is doing a projection, in this case account.customer name, then we should revise what we are actually propagating upward from the leaf level, from the relations, to include only the keys that will be, or the columns that will be included in the join, and the columns that are being projected. Obviously, it does not make sense to only propagate upward the column that will be finally projected, because the join to be performed, I need the common column between the tables that are being joined. So customer-name is in the account table. So I will start by considering that I need to propagate upward customer-name. But this is not the only column I need. I also need a column that will enable me to join account and branch. So I will project customer-name and also can you guess which one? It's going to be account.branch_ID. I need to propagate that one up as well. So you might argue that, well, we're not really saving here in terms of hard disk access because we are going to open the page anyway of the table to get the column we're going to project. And the answer is yes. You got that right. We're not going to save in terms of the number of pages we're going to read. It's still the same amount of hard disk work. But we are saving something else here. We are saving the space in memory. So let's imagine that account has 15 columns. If I only, when I open the page, read 2 columns, or perhaps 3 for join purposes, 1 which is customer-name, and maybe another 2 for doing join, and I propagate upward, or I keep with me in memory those 3 columns, the SQL statement is gonna, while executing, is gonna take less memory. So instead of having to keep all the 15 columns, now I will only keep 3 columns, and I don't need the other 12. So pushing projection down does not necessarily, and actually in almost all cases, it will not save you hard disk access, but it will save you in the memory. And this is an important issue because at any point in time, the database engine could be executing many SQL statements at the same time, at the same instance, and you need to be as conservative as possible in your memory usage. And this actually is the case when you consider only the columns that are of interest, which are the ones being projected and the ones used or required for the join. For example, from branch, I only need branch.id and branch.branchCity. I don't need anything else. So there's no need to actually propagate the rest. And this follows generally for all queries, that if there is any opportunity that I push projections down, then we should do that, just like we pushed selections down. As a final note to this slide, the tree on the right is not the one that you will actually see if you have already pushed projection down. So I have put an X there to inform you that actually that will not be the picture. You will project down from account, customer name, and branch ID. So the last node at the top, it's going to be a join operator, and the projection would have been done down in the tree, as I already mentioned. The third heuristic is perform most restrictive join and selection first. Now, let's talk about the restrictive join, and the selection will become clearer as a consequence of that. If you look at the tree at the left in the slide here, I'm joining account with a depositor, and then later I join it with branch. I could as well have joined branch with account, and later on in the above level joined it with depositor. Now the question is there a difference in terms of performance, or in other words, number of rows propagated upward? And the answer is yes. It depends on the number of rows you have in the table. The fewer we propagate upward, the better. So let's look at the example I have put here, the numbers at the bottom right of the screen. If branch has 600 tuples, and account has 600 tuples, and depositor has 300 events or tuples, so 300 times someone went in and made a deposit. Now, if there is a balance between those tables, which means the data is evenly distributed, I mean by that on average, if I say I have 100 branches and 600 accounts, on average I have 6 accounts per branch. And if I say that I have 600 accounts and 300 deposits, then on average 1 out of every 2 account holders made a deposit. Then I can start to rationalize about which join will propagate upward a smaller number of rows. Now obviously there is an issue here. I'm assuming something that might not be true, but let's just wait on that till the slide after next. So if we work out our averages, again I'm assuming here that the tables are connected in a balanced way to each other. So if branch and account have a common column, foreign primary thing, then my assumption is that when I join branch and account, I should get 6 rows. In other words, again, every branch has 6 accounts. Similarly, when I join account and depositor, I should get 2 rows. The calculation here is simple, and it's not really maintaining any statistics about the data. It is just, again, using the number of rows in the table. Now, the big question here, is this a valid approach? And let me move to the next slide to show you that there is another scenario that we're not considering here. Here is actually a different way to think about it. The extreme kind of scenario, or the worst case scenario if you like. What if all the accounts were in one branch, happens to be the Brooklyn branch, and all the other 99 branches have no accounts at all? Or what if there is only a single account that made the 300 deposits? So now my averages that I computed in the previous slide are not representative at all. The problem here is that, or the problem are stemming from the fact that I am only using the number of rows in the table to predict what is the average number of rows in the result set from joining those two tables. In other words, I'm guessing the number of rows in the result set from just looking at the table sizes. But we know that it's not necessarily enough to actually come up with a good answer. We need more. And specifically because of this third heuristic, and the first two, they make a lot of sense. We're for sure propagating upward smaller number of rows. But with the restrictive join, without any statistics about what exactly exists in the column, maybe the column is full of duplicates. So your assumption about the size of the propagated result set, intermediate result set, is going to be completely either an undershoot or an overshoot from the actual result. Because of this, researchers developed cost-based optimization, which we are going to look at as the next technique. Now, you might be wondering by now, like, how do we generate these trees? How can I, given one relational algebra tree to start with, I end up with a number of relational algebra trees that will produce the same result, but they are actually arranged differently in terms of the joins and the selection and so on. And here I would remind you with the stuff you've learned in Database 1, specifically what's called equivalence rules in relational algebra. I will put a handout on the MET website that's kind of a refresher of what you can do to a relational algebra tree to transform it to another equivalent one that will produce the same result set, but is arranged differently. And I expect you to have learned this material in Database 1. And although I don't necessarily ask questions in the exam directly about it, because again, this is Database 1 material, but it is required for understanding and working with Database 1 material, but it is required for understanding and working with or generating different relational algebra trees as part of the optimization topic in this course. And these revision slides will be available on the MET website. Okay, so to summarize, the three heuristics are applied to the relational algebra tree to try to reduce the number of tuples propagated upward in the tree from the input relations at the leaf level. You're going to push selections down, push projections down, and perform most restrictive joins and selections first. Okay, so let's move on to cost-based query optimization, which is the more modern approach of doing optimizations. The idea here is that we're going to generate many relational algebra trees, and we're going to compare the cost of running each one of those trees without running it. Obviously, it doesn't make sense to try to run them all to pick this, the one that has smallest number of manipulations or I/O manipulations, because you've run more than what you want. So we'll just generate them and estimate the cost of running every plan and pick the minimum. Okay? Now, what we're going to do, or what a database engine does to do this, it keeps statistics about the table. It's stored, these statistics are stored inside the database engine, just like the data is stored inside the database engine. Okay? The stats that gets kept are number of rows in a relation. We've already used that in the heuristics. The number of bytes in each tuple, the number of blocks or pages that every table uses or is stored in. So if you have an employee table that's stored in 50 pages on disk, B of employee is going to be 50. Okay? And a very important, the number of distinct values that appear in every column. Okay? And it's usually written as VRA or VANR. Okay? The number of unique values in column A in table R. And that might be a little bit surprising, because you would say, like, that's like a lot of stuff that gets kept. This one is makes sense, sure, But when it comes to VRA, it's like, okay, that means every time you do an insert, update, or delete, the number will be actually updated. And my answer is yes or no. Yes and no. Yes, it's updated. No, it won't be updated right away. Because if it's updated right away, that would be really a performance burden on the database engine. Okay? So we will see when does it get updated. And the rule is going to be like you update it when the traffic to the database engine is low. So if people at night, for example, they go and sleep, and the traffic to the database engine, if it's behind a website like, you know, an e-commerce website, the traffic is much slower or lower than during daytime when people are making orders. So then you can go and update your stats by figuring out the number of unique values in every column. Okay? So let's see an example. So I have here a naive table R that has 4 columns, A, B, C, and D, and this is the content inside each column. Now, the T of R, or the number of rows in the table, is 5. The number of unique values in each one of the columns is written over here. So VRA is 3. The number of unique values in column A is 3, cat, dog, and bat. Number of unique values in B is 1, obviously. And in C, it's 5. And in D, it's 4. Okay, so that's VRD is 4, obviously. And in C, it's 5. And in D, it's 4. Okay, so that's VRD is 4. Okay? Okay? And if I know about the size of every column, then I can figure out what's the size of the row, which is 37 bytes, summing up these numbers. Okay? So, this is what we're going to do. This is how cost-based optimization works. Cost-based optimization relies heavily on statistical estimates. It's not an accurate number. Sometimes, like for example, in the one we're looking at in this slide, it's going to be an accurate number, but in most of the cases, it's not going to be the exact number that you get in the result set. It's going to be an approximation. It's just an estimate, okay? So if you remember your Mass 4 stuff, you know what an estimate is. It's just an estimate, okay? If we run it for an infinite number of times, that would be our average, basically, okay? So let's look at one where the estimate is actually the actual number. If I'm doing cross product between two relations, R1 and R2, now remember a cross product works like this. You're going to retrieve one row from R1 and pair it with all the rows in R2. And then you retrieve the second row in R1 and pair it with all the rows in R2. And this goes on. So the total number of rows, T of W, is going to be T of R1 multiplied by T of R2. Because I'm doing this blind pairing between the rows in R1 and the rows in R2. So if this has 5 rows and this has 10 rows, cross product means I'm going to get 50 rows. And that's what this is saying. The size of R1 multiplied by the size of R2. Now, I mean the size here, sorry, the number of tuples in R1 multiplied by number of tuples in R2. Now, the size of W is going to be the size of R1 plus the size of R2. Okay, this is not a join. So I'm doing blind pairing between rows from R1 and a row from R2, or row from R1 and a row from R2. So if R1 had 5 columns and R2 had 8 columns, I'm going to be having a table of 13. 5 plus 8 is 13. So I'm going to have 13 columns, and consequently the sizes is going to be the same. Just the size of a row in R1 plus the size of a row in R2 will make me one row in W. Okay. Now, let's look at the more interesting one. We'll start seeing estimates. So, say I get a selection. The query is select star from R. Sorry, select star from R, where column capital A is equal to some small value, some value small a. Okay. So the query again is select star from R, where capital A is equal to small a. Now, since this is select and there is no projection, I'm saying select star, the size of W, the size of the set, the size of the result set, W, is going to be the same as the size of R in terms of the row size. So S of W is equal to S of R. Now, the important question here is how many rows will be in the result set? What's T of W? Okay, and here we start seeing the estimates I was referring to before. Okay, remember, I have with me statistics about how many unique values exist in every column. And here I'm querying a specific column, which is A, the one we've seen in the table before. Okay, the one that has cat, dog, bat, and so on. So the general rule is, I'm looking for an estimate. So and I wanted to have it as, as accurate as I can be. So I will use my stats, the number of unique values, and I will use the number of rows I know that they do exist in the table to get an estimate of the size of the result set without actually looking at the specific value of val. Okay? Now, why am I doing it that way? Because this is the fastest way I could do it. Because if I start looking at the specific value of val, I might slow things down. It's almost like as if I would like to run the query now to figure out how many rows will come out. Well, if I run the queries, then I've run the query. Then I don't need to worry about it. The point is the question of how many rows will come out will be meaningless because I've run the query. So I don't want to run the query. So I'm not really interested in a specific value for val. I'm asking for any value for val. What would be on average the number of rows in the result set? Okay? So if actually I was querying this column and val was cat, it would have been 2. And if I'm querying this column and val is dog, I would have got 2 rows in my result set. And if my val was bat, okay, then talking about corona, if my val was bat, then the result set size would be 1. Okay, but I don't want to look at the val. So this is what I'm going to do. I am basically asking, if you'd like to think of it as, in terms of mass for stuff, what's the probability that this row will go into my result set? Okay? Any specific row. So this is what I'm going to do. I'm going to use the following formula to get an estimate of the number of rows in my result set doing this exact value selection. It's going to be 1 over VRZ. Okay? So if my query, if the Z here is on A, that's going to be 1 over 3. Okay? Why? When I run a query on A, here I'm assuming, by the way, that what I'm looking for does exist. I don't think about the case where, I get a val that does not exist in the table because the result set is going to be 0 anyway. Okay? I'm thinking always about the case where the value exists in the table. Now, if I'm running the query on column A, and since what I'm looking for indeed exists, then it's going to be 1 out of 3, a cat, dog, or a bat. Okay, so it's going to be 1 over 3, 1 over this 3, 1 out of the 3 possibilities basically. But if I just answer 1 over 3, the problem is this does not relate to the size of the table, because this table could have 5 rows like here, or it could have a million rows. So if I just answer 1 over 3, yeah, I have 1 of 3 choices, okay, cat, dog, or bat. But that's not good enough, so I'm going to weight it by the total number of rows. I multiply it by total number of rows. Okay? And this is applicable to all columns. Okay? So if I get a query on A, it's going to be 1 over 3 multiplied by 5. 5 is the number of rows. Okay? If I get a query on B, it's going to be 1 divided by 1 multiplied by 5. If I get a query on C, it's going to be 1. If I get a query on D, it's going to be 1.25. And note here, these are estimates. Like there's There's no result set called that has 1.6 rows or 1.25 rows. It's just an estimate. Okay? How do I calculate the estimate? Again, according to this formula. 1 over the number of unique values, because my query will hit one of them, because this is exact value query, so it's going to be one of them. It's either cat, dog, or bat if it's A. It's either A, B, C, or D if it's D. Okay? So here the val will take one of these guys. Okay? So it's going to be 1 out of them. So that's why it's 1 out of 4. Okay? Because the A is repeated. Okay? Multiplied by total number of rows. And the nice thing is when I multiply by total number of rows, now I have a more accurate estimate, because if I have here 1 million rows, this number is going to be 1 divided by 4 multiplied by a million. So you're going to get out, on average, 250,000 rows. Okay? So this is our approach. This is how we estimate things. Notice that this number is not exactly what we get. Again, if we run it here, it's going to be 2 rows, and 1 row. But on average, 2 and 2 and 1 is 1.6 on average. So if you keep running it forever, then it's going to be 1.6. Now, obviously, here there is an assumption, which is that the chance of querying a value is the same as the chance of querying any other value. If you build this table, and from here till infinity, you're always running it with z equal to cat, you're always getting 2. You will never see the one case where you run it when the val is equal to bat. But this is not what we're trying to serve here. What we're saying here is that the chance of querying any value is the same as the chance of querying any other value. So as you run this to infinity, on average it's going to be 1.6. Okay? So this is what I try to highlight in my previous explanation. We are assuming here is that the values are uniformly distributed, okay, over all possible values. Okay? I don't have bias in my queries here. Now, there is another assumption, or another way to do this, okay, which is, if the database engine knows about the domain of a column, it would use it instead of counting the number of unique values. And this is actually the reason why one of the good guidelines for writing SQL, if you can come up with the domain for a column, you should actually include it when you are creating the table, in the create table statement. Let's say you have a column called colors, and you know that you are actually will never have anything but red, green, and blue. So when you are creating the table, you can add that as a constraint that for this column, the values are going to be in red, green, and blue. Same thing for gender, it's going to be male or female. Okay? It's not the varchar of 6 letters, because varchar of 6 letters will include all combinations that could be put in 6 letters. But if gender, you will only have male and female. So if you're worried about the database engine spending time maintaining statistics, and you don't want to be running with old statistics, because sometimes that will happen, then your other alternative is to define domains on your columns. That's if you can. Sometimes you can't. Like, for example, names, first names. Okay? Well, you could try to enumerate them. You could say, okay, I'm going to enumerate all names of people in Egypt. But you get someone who's calling his name Hammo. Okay, how would you, how would you have predicted that one day we will have someone called Hammo? Okay, so you got the idea. Like, you cannot enumerate certain things, but you can enumerate other things. Like, you can enumerate age. Okay, that's going to go from, say, 0 to 125, 130, 150. Okay. Unlikely to see someone whose age is 500 years. So you can enumerate certain things, and if you can enumerate them, you're helping a lot the database engine, because it does not have to track the number of unique values. It will be, the number of unique values will be the size of your set. So in the case of gender, it's going to be male and female. Okay, so it's going to be 2. In the case of colors, red, green, and blue, the number of unique values is going to be 3, and so on. And I'm showing you here calculations. The same calculations we've done before, but with the domain size instead of the number of unique values. Okay? And you can see the numbers obviously changing because I'm having here a different number of domain sizes. So domain of A is going to be domain of the column A in relation R is going to be 6. Here, before we had it 3. Let's say, you know, you're building this database engine for a pet shop, and you ask the pet shop owner what kind of animals you trade in, or possibly you would ever trade in. So I give you a list of 6 animals that he focuses on in his business. That would be your domain size. Okay, 6 of them: cat, dog, and bat, and mice, and snake, and whatever. Okay. So you could do that. And again, this is a hint into how you can enhance your SQL by including domains with every column when you create the table. Okay. And this is a comparison of the 2 calculations we looked at. What we are describing here, you will find it called in the textbook selection cardinality, which is the size of the result set coming from a selection operation. Okay? Now let's move on. Let's see something a little bit more involved. So what we're doing here, we're having a query that says select star from R where this column is greater than or equal to some value. So it's not an exact value query. It's not Z equal to val. It is Z greater than or equal to, or val, you know, Z greater than or equal to some val. Okay, so there is more than one entry in your acceptable in your result set. Okay, so if we say greater than or equal to 10, and you have values that spans from 5 to 15, so greater than or equal to 10, so 10 is included, 11 is included, 12 is included, 13 is included, 14 is included, and 15 is also included. Okay, so now we would like to estimate the size of the result set if you have such a query. Okay. And historically, this has been, you know, like an interesting activity for researchers. So there are actually 3 solutions that people have adopted. Remember, we're just estimating things. We're not really after the accurate number. Okay, and as long as you apply the same estimation when you see the same operator over and over, then you're going to be in a safe situation. You know, you might not be exactly, you know, working with accurate estimates, but what you're doing is you're applying the same technique over and over again. So if you have an overshoot and you keep applying the same technique, you're always overshooting, and that means you're not really effective. The problem is when you overshoot and undershoot in the same operator. Okay, so historically, one of the first solutions that was proposed to estimate the size of the result set here is to say that the size of the result set will be half the size of the input relation, half of R, which is what's spelled out here. The T of W, number of tuples in W, is going to be half multiplied by T of R. Okay? Now, a second solution that researchers also adopted and some database engines followed, which is that the size of W is going to be 1/3 of the input relation. So 1/3 multiplied by T of R. So let's try to rationalize where are these ratios coming from. So in the case of half TR, the rationale goes like this. Let me just change my pointer. Let's say you have a column in a table, you're running this query on greater than or equal to val, and the column spans from 10 to 20. And there are no duplicates. So you have 2 extreme cases. If your val is 25, if your val is 25, your result set size is 0, because there is nothing greater than or equal to 25. If your val is 10, your result set is n. Okay? So on average, and obviously, you know, you could put values in the middle here. On average, it's going to be half. Okay? Because you will have 1 and 2 and 3 and 4, so it's going to be half n. Okay? So that's why this ratio could represent an estimate as you run it to infinity, this query, okay, this query, as you run it to infinity, for different values of val, okay? Now, if you have duplicates, 1/3 is actually the more accurate estimate, because if you have lots of duplicates for all the values that exist, for example 10, and then 10, and then 11, and then 11, and then 12, and then 12, and so on, the size of the result set on average is going to be 1/3 the size of the table. Because what the duplicates do, even though they will increase the size of your result set because of the existing of duplicates, you are also missing some rows from the table more than here, more than in the first approach, because there are duplicates that you don't include in the result set, and they are part of the table. So on average, it's going to be 1/3, okay, because of the existing of duplicates you don't include. That's why the half decreased to 1/3. Okay, while there are still duplicates that you will include in the result set, but think of the duplicates that you will not include in the result set. Okay, and you can just work out with these numbers between 10 and 20, have every number here duplicated 3 times, generate this list, and try a number of queries, and you will see that the size of the result set, actually you can do that as an exercise, you will see that the size of the result set is going to be a little bit smaller than half. Okay, it's going to be approximately 1/3. Okay, now there is a more sophisticated approach to answer such a query, which is to keep, in addition to the number of unique values in every column, keep the minimum and maximum value. Okay? So when you get a query like select star from where z is greater than or equal to 15, if what you are querying exists, it's going to be within your range. And we said we're always focusing here on data that do exist. Okay? So here 15 is going to lie between 1 and 20. The question is, which portion of this extended range between 1 and 20 it lies in, or it falls in? So it's going to be in the last, you think, if you divide it from 1 to 20 to 4 segments, each of length 5, so from 1 to 5, 5 to 10, 10 to 15, 15 to 20, so it's going to fall in the last segment. Now, what you're interested in, because we are saying greater than or equal to 15, so everything in the last segment is with you in the result set, what we are interested in is to find out the proportion of this segment to the total range, to the whole range. Okay? Now, let me just go back. So I will take this number and multiply it by total number of rows. So if my T of R is 250, then I will get out an estimate of my result set size. T of W is going to be 0.3 multiplied by 250. Okay? And this is obviously a more accurate solution than the previous two, because the previous two we assumed in the first scenario that we don't have duplicates, and in the second scenario that we have duplicates, and we have duplicates with the same number of repetitions for every value, for all the values. So if I have like from 1 to 10, then and I'm saying that I have duplicates, so if 1 is duplicated 5 times, 2 will be duplicated 2 times, 3 will duplicate, if 1 is duplicated 5 times, 2 will be duplicated 5 times, 3 will be duplicated 5 times, and it goes like this. Okay, that's for solution 2 in the previous slide. Now, so obviously this is much better, because we are actually tracking, the segment that will go into our result set, and we are finding how much this represents from the total range that we have stored, and based on that we decide, okay, to or we use that ratio, which is coming out from this equation. We use that ratio, or basically this number, and multiply it by total number of rows to get a more accurate estimate. Okay. Now again here I'm assuming an equal distribution of the chance of getting a value is the same as the chance of getting any other value. Okay, like for example, if I say my minimum is 1 and maximum is 2, the assumption here is that I have the other values in between, or most of them. But that might not be necessarily the case, but we're not going to go, beyond this when we talk about solution 3. Like for example, I could have the following. I could have 1 and then 14, 15, 16, 17, 18, 19, 20. But this is not the assumption here. The assumption here is that we have all the values between 1 and 20, or most of the values between 1 and 20, and the chance of getting a value is the same as the chance of getting any other value. Okay? To solve the problem we're describing here, which is, a lot of numbers are missing. And yeah, I have minimum is 1 and maximum is 20, but really the numbers are 1, 15, and the rest to 20. What do we do? Then we will see something else towards the end of this lecture. We will see histograms where we can solve this in a much better way. Okay, let's move on. So, what is the estimate of select star from R where z not equal to a val? So I will want everything except 1. So if I have a table that has 10 rows, and the column I'm interested in has numbers from 1 to 10, and the val that I'm querying here exists, so it's going to be from 1 out of these 10 numbers, from 1 to 10. So if I say select star from where z not equal to 10, I will get 9. From 1 to 9, I will not include the 10. If I get select star from where z not equal to 5, so I will include 1 to 4 and 6 to 10. What that means is my result set size is almost the same as the table size minus 1. And for that purpose, I will just ignore it. I will just ignore the minus 1. I will say that my T of W is equal to T of R. Okay? I will say that it's the same size. It's not entirely true. I mean, but remember, this is an estimate, so it's okay. We can get away with it. We can say, okay, it's going to be the same. What about this guy? We have seen before in the first few slides, this is the distinct operator. Okay? Now, if the table has no duplicates in this column A, then I will get the whole table back as the size of my W. If the table is all duplicates, okay, then I will get an empty result set. So on average, half will be omitted. That's the rationale here. Again, remember, this is an estimate, okay? So on average, half will be the size of my result set, which is the zero, between the 0 case and all the number of rows is going to be half. And this will be our estimate. Again, I know some students, when they hear this, they will be a bit kind of confused and say, okay, like, not necessarily half, but maybe something else. And remember here, this is an estimate as we go to infinity, as we keep running this, as we go to infinity. So there will be many data that we try with. The data will be updated. Number of duplicates will change. So if we run into a table at one point in time from here till infinity where all the rows have the same value, they're all duplicates, the result set is 0. And the data will keep changing, and then we'll run in one point later on in time with all the data unique, so we'll get the whole table size. So as we run to infinity, on average, we're talking about half TR. Okay? This is the rationale here. What about combined terms, like select star from R where A equal to value 1 and B less than value 2. So I'm creating here 2 columns. Okay? Now, the trick here is in the operator, not in the terms. This operator is an AND. This is an AND. This is very important here, okay? This is an AND. So the rows that will come out and as will go into the result set has to satisfy A equal to val 1 and B less than val 2. Okay? What we're going to do is, let's compute the estimate for every term separately. So A equal to val 1, this is an exact value estimation, so it's going to be 1 over the total number of unique values and A multiplied by total number of rows. You see over here that I have here total number of rows in total number of unique values in column A is 50, total number of rows in this relation is 10,000. So if I'm saying A equal to val 1, it's 1 out of the 50, so 1 divided by 50 multiplied by 10,000. Now, I will assume here for in this specific example that B less than val 2, I will work with the 1/3 estimate, and that's what you see here. So this term alone is going to be 1/3 of R. Okay, if my query selects star from R where B less than val 2, let's say I'm going to use our solution 2, the one I refer to as solution 2. So it's going to be 1/3 of R. Okay, we said solution 1 is half of R, solution 2 is 1/3 of R, a little bit more conservative, and solution 3 is the one we kept the minimum and maximum values. So I want to complicate things here, so I'm just going to say 1/3 of R. Okay, but the question is, how do we combine the estimates? So the estimate to this alone, it's 1 over 50 multiplied by 10,000. The estimate to this alone is 1/3 multiplied by R. So how do we combine them? Now, the trick is in here. This is an AND. It means that the row that go into the result set has to satisfy this one and this one. Okay? So here's what I'm going to do. I will just run it from left to right. Okay? If I run this one first, I will get this. 1 divided by 50 multiplied by 10,000. Okay, that's 200. Now, what I'm going to do is I'm going to say, okay, and I want those rows that are, those 200 rows coming out from this guy to also satisfy B less than val 2. Okay, so I will imagine as if actually my table, I'm not going to do the 1/3 on R, I'm going to do the 1/3. That's why I said I'm going to process it from left to right. I'm going to do the 1/3 on the table or the result set coming from this first term. So it's going to be 1/3 of 150 divided by 150 multiplied by 1 over 50 multiplied by 10,000. That's why I have here this. Okay, it's multiplied by 1/3. Okay, because the term here is an AND. It's this one, this term, and this term must be satisfied. So I will work it left to right. We'll solve this one first. I know now that the result coming out is going to be 200 rows as an estimate, and then I have to apply this on them. And since we said we're going to use 1/3, it's going to be 1/3 of whatever coming out. So it's going to be, 200 multiplied by 1/3, which is 67 rows. So the estimate to this query is 67 rows. Okay? And what about OR? Now again, I will do every one first. I will think of every one of these terms separately. This is going to be again 1 over 50 divided by 1 over 50 multiplied by 10,000, sorry. I will adopt the rule of 1/3 here, but since this is an OR, what that means that all that match this term from R and all that match this term from R, again, all that match this term from R and all that match this term from R are part of my result set because it's an OR. Okay? So it's going to be all that match this from R is going to be 200. All that match this from R is going to be this much, this number. Okay? 1/3 of 10,000. And I add them up. Okay? So this is an addition. That's why you see the number 3,533. Again, because this is an OR. Anything that matches here or here is with me in the results. This is the rationale of the word or the term OR. Okay? Okay. Let's look at another big one, which is the join. Now, very, very important because most of SQL is about doing joins. Why? Because to avoid data anomalies, we do normalization all the way till third normal form or Backus-Naur form, and then we've split the data into these tables that are completely disconnected from each other except using the foreign primary key relation. And then when we would like to construct meaningful data, again, we're going to do joins to, you know, extract or create data from multiple tables. So join is like the essence of SQL, okay? Most of the time we're doing joins, so this is very important, okay? Now, how do we do a join? Now remember, a join, you cannot do a join unless you have some common column, or at least, you know, for the useful joins or the efficient joins, you have to have a column from here and a column from here that is somehow linked, okay? So, let's say, you know, I have a set of attributes in R1, a set of columns, I'm going to call them X, and those in R2, I'm going to call them Y. If there's no intersection between X and Y, I'm really doing a cross product. Okay, we've talked about that early on. What's the estimated size of a cross product? So we're just going to skip this one. It's a trivial case. Let's go to case 2. Now, in case 2, there is a common column between R1 and R2. As you see in these lecture slides, it's going to be this A and this A. That's why I have the same letter. So I'm joining on the two tables, R1 and R2, on A. Okay? How does this work? Here, we have to go back to database 1 and remember this concept that's called containment of value sets. Okay? What is this, you know, statement saying? If the number of unique values in column A in R1 is less than or equal to the number of unique values in column R2 in table R2, then every value in R1 is in R2. Do you agree on this? Let's read it again. I'm saying that if the number of unique values in column A in R1 here, okay, here, is less than or equal the number of unique values in R2 here. I'll put you some numbers. Let's say I have here 3 unique values. And if this rule holds, then this could either be 3 or 4 or 5. Then in other words, every value here in R1, R1.A, must be in R2. Okay, dot A. That's one scenario. There is another scenario, which is the opposite of what I just described. If every value that appears in R2.A appears in R1.A, and the number of values in R2.A is less than or equal to the number of values in R1.A, then it's the opposite scenario of what I'm describing. Okay? This is called containment of value sets. What is this trying to relate to? You see, you have a table that has a primary key, and then you would like to link it with another table that's referencing this table. So for the other table, you're going to define what's called a foreign key that references the primary key in the first one. Okay? Unless you have some data anomaly, whatever appears in the foreign key column must appear in the primary key column. Okay? If you see the number 10 in the foreign key, it has to appear as a primary key in the other table. Okay? This is called containment of value sets. That one of them is contained in the other. Okay? The foreign one is contained in the primary. Okay? This is what we're trying to say here as well. Okay? Right. Why are we interested in this? Okay? Well, let's look at this case. When, if I can just find my pointer, yeah. Let's look at this case. When the number of unique values in R1.A in this column is less than or equal to the number of unique values in R2.A. What does this mean? This means this is the foreign and this is the primary. Because the number of unique values here could be less than what's in here. So this has to be the foreign and this has to be the primary. Okay? Now, what you do in the join is that you're joining on these two columns. So you're going to write something like R1.A equal to R2.A. Now, how is this evaluated if you think of it stepwise? We are going to grab a value from here. Let me just go to my nice pointer. Yeah, I like this pointer more. Okay? No, it's not this one. No. Okay. We are going to grab a value from R1.A and go and search for it over here in R2.A. If we find it, and we will indeed find it, because this is foreign and this is primary, when we find it, we have found one row in our result set. And then we go again and pick another value from here and search for it over here. And when we find it, we include it in our result set. Let me try to write some symbols so we're on the same page here. Let's say I have here X and Y. So I'm going to grab the X because it happens to be in the first row here, and I'm going to go and search in R2.A. And then I grab Y and go and search in R2.A for Y. Okay? And I will find them because, I mean, this is a foreign primary thing, so I will find them. So I'm just going to, just to enforce the point, here is the X and here is somewhere the Y. Okay? So I will find them. But what am I just doing? If you think of it, grabbing the X and looking up over here, it's like running a query on this guy where I say select star from R2 where A is equal to X. And then when I'm looking for the Y, it's like saying select star from R2 where A equal to Y. Okay? So we're basically doing exact value queries, but we're doing it multiple times. If we go back here, this is this was foreign, this is primary. If we reverse it, this is foreign, now this becomes primary. We're going to do the same logic. You can verify that by looking back at this slide 57, because at the denominator down there, you can see that we are searching in the bigger of the two, because we have to. I'm picking from the foreign and I go to the primary and search in it. But the bigger of the two is going to be the primary. Okay? Now we could repeat the same calculations, just like we've discussed before, but for domains. So I'm going to skip this slide. You can read it on your own in the lecture slides. It's the same logic we have been discussing, just the domain will help us instead of tracking all these unique values. Okay? Now, in all cases, the size of W is going to be the size of R1 plus the size of R2 minus the size of the column, because we don't repeat the column, we're doing the join in. Like the A that we've been using, we just have it once in the result set, not twice. Okay? Now, what about more realistic SQL statements where you have things combined, like, you have a select and a join? This is what we're going to do. We are going to do a stepwise approach where we estimate one term and then continue on doing the rest of the work as if the one term that we actually estimated created for us a temporary table that we know its properties. So for example here, I'm doing select A equal to small a from R1 and I'm joining with R2. So there's nothing frightening here. I will treat this as a separate SQL. I want to estimate what's the result set of this table, the result set coming out from this expression. So this is going to be 1 over the number of unique values in A multiplied by total number of rows in R1. This is one of the unique values in A, R1.A. 1 over that multiplied by TR1. And this will be the size of this temporary table. I'm calling it U. And the S of U is going to be S of R1, because I'm not doing any projection here. And then I will do U joined with R2. Okay, so I have here the important term that I need to work with. Okay, and this will continue on. Now, even here, really nothing here now surprising. I'm having a join between three tables. R1 and R2 are joined on B, R2 and R3 are joined on C. As long as I have my stats, I will do it in stepwise. I will do R1 with R2. Okay, so I have here my stats that I need, and this is the number of unique values, so it's going to be TR1 multiplied by TR2 to estimate the size of the join, that is the size of the result set coming from the join. So it's going to be TR1 multiplied by TR2 divided by the maximum of the two, which is 200. That will give me a new table U, and then I will do a join between U and R3. Okay, so this is my U with the different parameters. Okay, and then I will join it with R3. Okay, now you can check the numbers and you see that actually everything is according to what we have been describing. Okay, so we can do stepwise approach to answer or get an estimate for a complex query that has many terms. We just do it usually from left to right, and it will work out nicely with these substituted intermediary tables. Okay, now long story, let's put things together. So this is what we're going to do. Going back to our simple example, you have here this example got translated to logical tree. We somehow magically, we didn't talk about that yet, how do we actually generate all these guys, except I told you that you could use equivalence rules to actually make sure that the new SQL tree the new relational algebra tree that you are producing is equivalent to the initial one that you start with, to make sure that you will always produce the same result set. But I really didn't go beyond what I mentioned there. How actually, or how many possible trees exist? There are many, but just looking at these two, okay, I'm just going to give you an idea about what actually happens in a database engine in terms of the cost estimation. So now you know how do we do the estimates for all the operations. Okay, we've talked about exact value, we've talked about duplicates or distinct, we've talked about joins, we've talked about not equal to, we've talked about range queries. So let's say from this initial relational algebra tree, you managed to generate these two. And now we want to figure out which one is better in terms of performance. So what you're going to do is you're going to run our cost-based estimation techniques that we've been discussing. Now to do that, you must have the stats with you, and obviously you will have them in the database engine. So here are the stats: number of rows in R is 5,000, number of unique values in column A in R is 50, number of unique values in column B in R is 100, and the same thing for table S, which is the B and the C columns, because this is what you're doing the join on. Okay, so I start with R equal to 5,000, I do a select A equal to 10, I will estimate that the size of the result set coming out from this selection is 100. How did I do that? It's going to be 1 over the number of unique values in A. Here it is. So it's going to be 1 over 50 multiplied by total number of rows in R, which is 5,000. So it's 1 over 50 multiplied by 5,000. So give you 100. Okay. Now, I'm doing a distinct operator. We said it's going to be half. So the 100 becomes 50. Now over here, I start with S being 2,000. I do a distinct, so the 2,000 becomes 1,000. This is the estimate of the size of the result coming from applying the distinct operator. Okay? And then I do a join between this temporary table and this temporary table of 50 and temporary table of 1,000. I will apply my formula, so it's going to be total number of rows here multiplied by total number of rows here divided by the maximum of the values in the number of unique values in the two columns I'm joining on, so I get 250. You can apply the formula later on, okay? I'm sure you've got it by now. Or this is one alternative. Now another alternative to this SQL or to this relational algebra tree is this one. I do a select, it's 100, and then I do a join right away. So it's 1,000, applying my formulas to estimate the join, and do a distinct elimination, so it's going to be 500. Okay, half the 1,000. Now the question is which one to pick. So this is what we're going to do. Okay, I will sum all the inner nodes, as it says here. Sum all the inner nodes. So the 100 plus 50 plus 1,000 give you 1,150. 100 plus 1,000 give you 1,100. Obviously this is a smaller number, so I pick this tree. I'm ignoring the sizes of the tables because I'm feeding the same tables to both trees, so there is no point in computing the sum with the sizes of the tables. I have to read these tables S and R anyway, so I don't need to add them up. But what is different here is someone would say, okay, but why don't I add the size of the result set? This is actually the final result set at the root level because we process it from bottom to top. So I just added the 100 and 1,000. I didn't add the 500, and I just added these three numbers, 1,000, 50, and 100. I didn't add the 250. The question is why? And actually, there's even a more subtle question, which is also related, is like, why are these numbers different? This is, if I'm sure you're convinced that this and this and this tree is the same thing. The three relational algebra trees are for this query. They're supposed to give the same result set, and they will indeed. If you run this one or this one or this one, you will get the same result set. But we are doing something here that is a little bit inaccurate. What we're doing is we are working with estimates. And as you keep adding up estimates and we work with estimates, you accumulate what is called in statistics errors. The more flawed the number you work with, or the numbers you work with, the more flawed the result. So the size of the result set, the final computed size, the 250 or the 500, has the highest accumulation of errors. So we ignore it, because if we actually add it up, we are basically adding up the value that we suspect that it has the most errors because of our estimation overshoot and undershoot. So we will just ignore it. Okay? The difference is really coming from estimation errors, or generally different estimation strategies, which produce different errors. Now, so we're just going to ignore this guy and this guy. And we'll sum up the intermediate ones, the intermediate numbers. And the one that has the smallest sum will be the tree that we run with, that we actually pass to the physical plan builder. Okay? Now, so the takeaway, database engine maintains statistics about each relation and also its columns to pick the relational algebra tree with the minimum estimated sum in internal nodes. You've just seen that. Now, let me give you an extension about actually how database engines do things. Okay, everything we've described is usually done, and even a little bit more. This is the a little bit more that you will see in advanced database engines. What advanced database engines do, they don't just keep track of unique values, they actually build histograms on every column. Now, this is an example histogram on a specific column called age. It tracks how many entries within every range. So, obviously here the entries vary from, or the row values, or the column values for the age vary from 1 to 25. There was no one older than 25. So it will track how many in every segment. So here are the values. Between 1 and 5 years old, we have 45 users. Between 6 and 10, we have 35. You can see that, it's almost 35. Between 11 and 15, it's 25. Between 16 and 20, it's 48. And between 21 and 25, it's 12. So if you insert a new row, let's say with someone who's 24 years old, this number will be incremented to 13. Okay, so you have 13 users or 13 entries where the age is between 21 and 25, but now it's 12, okay? And the total number of rows, obviously, in the table is going to be these guys, the addition of these guys. Now, what is this really trying to solve? It's trying to solve the problem that we're making a big assumption in just keeping the unique values, which is that the chance of getting any value is the same as the chance of getting any other value, that, you know, our numbers are uniformly distributed, okay? We don't have any bias in the data. And in many cases, it's not really realistic. Like, for example, if you think of the city where people live in Egypt, you know, we have like 30 million Egyptians or 25 million Egyptians living in Cairo. So in a table of Egyptians, 100 million rows, but in the city column, Cairo will be replicated 30 million times or 25 million times. So the distribution is not really even, okay? The chance of hitting any value in the city is not the same as the chance of hitting any other value. Actually, the chance of hitting Cairo is like, you know, 30% of the time, okay? So the number of unique values which we have been working with is nice and everything, as long as you have some kind of equal distribution of values. But if you don't, you run into an issue that your estimates are not really accurate, which defeats the purpose of, you know, the whole exercise of cost-based estimation, okay? So instead of actually just keeping unique values, histograms are kept for every call, okay? Now, so this is how this is used. If you get select star from or age equal to 12, you actually figure out the histogram that has the histogram bar that has the number you're looking for, which is going to be between 11 and 15. And you're told there are 25 values that's between 11 and 15. And since you're querying for 12, then that would be your answer as an estimate. So the, you know, estimate of this query is going to be 25 rows. Now, obviously, there is something here, okay, what if in the 25 rows or 25 values we had 20 11 and 1 12 and 4 15? So your estimate is an overshoot. But it's still better than using unique values, because now you have narrowed down the range that you're using to extract your answer from. So your answer using unique values, even though this sounds like sometimes might be an overshoot, as you keep running with histograms towards infinity, you're always producing a more accurate answer compared to number of unique values. But you can even do even better than this. If you keep the number of unique values in each histogram bar, so not the overall for the whole table, but for every histogram bar, okay? Like if you know that there are 3 unique values between 11 and 15, and what you can do is you can follow the same approach we have discussed before with exact value estimation. It's going to be 1 over number of unique values in this histogram bar, VH11, 15, or 1 over 3, multiplied by total number of entries in this specific, or values in this specific histogram, which is H11, 15. So it's going to be 1 over 3 multiplied by 25. And that means you have on average 8 rows in the results set if your query is select star from or age equal to 12. So histograms are becoming way more popular nowadays, and they're being added as an advanced feature in database engines because it enables us to estimate values of the result set size way more accurately. Because again, the assumption here is, you know, with just unique values, the one we have been describing earlier on in this lecture, assumes uniform distribution, and this is not really realistic. Okay? Now, and this lecture is a page that you should check that shows you how Postgres, which is the database engine you're going to use for project 2, inshallah after you finish project 1, how does it actually build the stats and what kind of stats it builds. So if you visit this page that will be accessible from the lecture slides, you can see all of this. You just need to log in, download Postgres, and log in to the shell, or download pgadmin, which is the graphical user interface for PostgreSQL. You create a table like this, 2 columns of integers, and use this script to actually fill in the table with randomly generated numbers. And then when you type at the command shell analyze, and you specify the table name, this actually command in Postgres, it will refresh the statistics. And if it has not been created before, it will create it. Okay? This is the stuff we've been talking about in this lecture, the statistics. And then if you go on and query this table, which is a system table in Postgres, pg_stats, and you specify the table name, tbl, and for this specific column, column 1, you will see the stats that was actually built from analyze. And if you look down here, you see it says the histogram bounds. So this is actually the histogram, obviously, because these are randomly generated numbers. The bounds have no meaning for us. I mean, it's not really a meaningful data, but we went and analyzed the data based on the randomly generated series of numbers, and it created some bounds for it. And if you see down here, it says element count in histogram. So I'm not sure why this is empty. I didn't have time to investigate yet, or, you know, usually it displays something here. Maybe it has to do with how I actually filled in the table. But it will display how many values. This is basically the number of unique values in every histogram bar. So you would see a set like this with a set like this with telling you, okay, there are, how many entries exist between 0 and 8, or between 8 and 20, and so on. Okay, so this is what PostgreSQL does, and this is what Oracle does. Way more better estimates than just number of unique values. And this is the reference with the textbook pages that you are required to read.